This is Math 145, Section 7.2 notes. Basically what we're doing here is just some applications, some examples of the normal distribution. We're also going to see some little bit more complicated problems where we're going to need to use the complement rule that we saw back earlier, or maybe other reasoning that just helps you answer a particular question. So back in 7.1, particularly the worksheet normal distribution that we did within the notes, we saw this idea. The fact that we don't have a table for every possible standard deviation and mean combination. So we don't have a table for every possible normal distribution. So what we do is we standardize our normal distribution. Whatever mean and standard deviation we are given, if it's normally distributed, we have this statement here, which basically tells us if we find these z-scores by taking our x value, subtracting off the mean, and dividing by the standard deviation, then that is also normally distributed. And so we have that table in the back of the book. Okay, it is also replicated on the last 2 pages of this set of notes. This is the worksheet that we did together, again, in section 7.1 notes. Why don't you take a second to do number 1A and pause me down, meet me back here. Okay, so we had a pediatrician whose 3-year-old patients had a mean height of 38.72 inches and a standard deviation of 3.17 inches. We wanted to know the proportion of her patients that are less than 32 inches tall. So here is my picture. I have, of course, your normal curve with the mean right there in the middle at 38.72. And then I just simply, as on a number line, drew 32 somewhere to the left of it. And I'm going to shade that area underneath the curve. And again, that's the area I'm interested in. On that next page, let's go ahead and find it. This is a picture of the normal table, similar to what you'll see in your book. We did use it again in 7.1 notes because we went a little bit into 7.2. Technically, the book doesn't get into this table until they get to section 7.2, but we've already seen it a little bit. Letter 1B actually guides you through that process, so go ahead and do 1B. Pause me down, meet me back here, and we'll talk. Okay, there's my work for my z-score, x minus mu over sigma. So my x value was that 32. Remember that goes first, and then subtract off the mean, divide by standard deviation. Rounding properly to 2 decimal places. Notice you did have to round that up to negative 2.12. Well, I guess technically, because it's negative, it would have been rounding down to negative 2.12. Okay, now let's go find that in the table. So you'll remember it's this z column here that you look for negative 2.1. And so you come down here and you find it in this column here, or sorry, this row here. And then the hundreds column, or the hundreds digits, from your z-score is in here in that 0.02 column. So that's how we get to the hundreds column. And right in that row that we saw before with negative 2.1 and the column that is associated with the hundreds digit of 2 gives you an area. And so I'm going to write that down here. Area under curve to the left of 32 is 0.0170, or 1.7% of patients, remember this was about pediatricians' patients, right, are less than 32 inches tall. Okay, that is that problem. How's that feel? Why don't you go ahead and try to do all of number 2? We've actually done something very similar to it on the last page of the normal distribution worksheet. So pause me down, try it out, and meet me back here. Okay, so I've done A and B here. Notice I did draw my table. I have it centered in where they told me the mean was. And I have 36 and 40 marked. And I want to know the probability that a randomly selected patient is between 36 and 40 inches tall. And so I shade the area under the curve between 36 and 40. Okay, now how are we going to find that area? We did do this, like I say, similar, something we did on normal distribution worksheet. It involves finding the area to the left of 36 underneath the curve and finding the area to the left of 40 underneath the curve. That will basically give us this area and also this area. And how do we get the area in the middle? To start you off on that road, I've done number B, which was to find the z-scores for both of those observations. And I've got those guys. Look those up in the table. And then think about what you're going to do to answer the question. Pause me down, meet me back here. All right, here is my work. So I went to the table and I looked up z equals negative 0.86. I found the area to the left of that under the curve is 0.1949. Now that is on the first page of the 2-page table. I then had to look up z equals 0.4, which is on the second page of that 2-page table. And the area underneath the curve to the left of 0.4 was 0.6554. So essentially what that does for me is it tells me to the left of negative 0.86, that area there is 0.1949 out of the total 1, as in 100%, right? Let me get another color here. Then we looked up 0.40, and excuse my scale, but it's not right. And now that area, all that red stuff, right? That area is 0.6554, right? Now, what am I looking for here? Right there in the middle, isn't it? So wouldn't that be the difference of those two areas? The red area there minus the yellow area. And so I subtract, and I get an area of 0.4605. So 46.05% of patients are between 36 and 40 inches tall. Lovely. Also want to point out a couple things. Number one, I stated my answer as the percentage of patients that are between 36 and 40 inches tall. Technically, the question asked for what is the probability that a randomly selected patient is that. So you could state your answer as the probability that a randomly selected patient is between 36 and 40 inches tall is 0.4605. Also, the second thing I wanted to mention is that I do a lot of work with these pictures. I have you draw these pictures a lot. Even though my math lab's not going to require it, I find that drawing out that picture really helps me understand what exactly I have to do next. It's not always find a z-score and find the area to the left of it. You know, look it up blankly and without thought. So drawing that picture and really making sure that what you need as far as the area in your picture and what you look up as far as the z-scores jibes, that's really, really helpful. I do not think I would be nearly as successful as I am with these problems if I did not bother drawing a picture. And again, my math lab's not going to require it, but dang, it sure helps. It sure helps, guys. Okay, here we are doing StatCrunch and TI calculators. Now, unfortunately, I'm sorry, I cannot do StatCrunch. There's something weird with the browser in my software I'm using here. So, but I highly suggest you go and you play with that on your own. But I am going to show you a video of me doing it on the TI calculator. And I'm hoping this video is a little bit better looking than the previous. Basically, we're just redoing the problem, right? So again, here is my 38.72, my mean in the middle, right? I've got my 36, my 40, and I want this area in between there, okay? This is the video of how to do that on my TI-84. All right, here's our VARS key. We used that back when we did Binom, PDF, and CDF. Normal CDF is the one we want here, and it is actually much closer to the top of the menu. So we're going to hit the second button and then that VARS key, which again is the distribution menu. And you'll notice you have normal PDF. Ignore that. You'll never use it. That is only if you want to graph the normal curve, and there's no reason for you to do that. So we want normal CDF. So of course I'm going to select that. I'm hitting enter. And then simply put, I'm going to put in my 36 and then a comma, my 40 and then a comma, the mean of the normal distribution. Notice we are not standardizing this. We can put in the mean as it's given to us, and then 3.17 for the standard deviation. And that is, again, lower bound 36, upper bound 40, mean of 38.72, and a standard deviation of 3.17 separated by commas. You've got to get those in that order or the computer will just completely misunderstand you, probably give you an error message in fact. So I'm going to hit enter, and poof, it tells me the area underneath the curve between 36 and 40. Perfect. My notes also ask you, did you match the value you got from the previous page? And you'll remember that that value was 0.4605. You'll notice, of course, it is not quite what we had, and the reason is because you'll remember that the table, the paper table at the back of the notes, of course, had to round all those values to 4 decimal places, right? Whereas the calculator doesn't have that rounding issue, and so they are a little bit more accurate. But you will notice that no matter if you do the problem in TI Calculator or through the tables in the book, they will both round to the same 0.46. So it shouldn't have any impact on the numbers of the answers that you put into my math lab, hopefully. So there we go. Okay, for example 4 here, we are talking about the 30th percentile. Percentile was talked about back in section 3.4, so it's possible that you need to review a little bit about that, or at least just look at the definition. At any rate, try to do number 4. How about all of it? Pause me down and see how far you get. All right, so this is what I did. I drew out for part A the normal curve and shaded the area in which we were interested. What we were looking for was the height of the patient at the 30th percentile. Thinking about the 30th percentile and what that means, we know from section 3.4 that that means 30% of patients are less than this height. And the question is, of course, what is that height, right? So we'll draw our normal curve. Again, we set it up like normal, and no pun intended. And we put 38.72 in the middle. And since we know that everything to the left of that middle mark is 50%, we know that the 30 percentile mark has to lie a little bit further left. And so I drew it about here, and then I shaded underneath it to picture that 30% area, or 0.30, right? And the question is, what X value gets me this area that's 0.30? So, as part B tells me to do, I looked in the body of table 5 to find an area as close to 0.3000 as I could get. In the first page of the table, you will find an area 0.3015 floating around in there. its z-value is, or corresponds to, that negative 0.52. Okay, for part C, we're going to convert that z-score into a value of x. We have been doing this the other way, right? We've had an x value, we then converted it to a z-value, and then looked up its area, right? Well, now we started with the area, went through the z-value score, and now we're on here to converting that into an x-value score. So I have this relationship, z equals x minus mu over sigma, that I know. I am simply putting in my z-value, my negative 0.52 that I got from above, and my mu and my sigma, and then I solve it algebraically. Multiplying both sides by 3.17 gets me up here on the first line over here on the right hand side, and then adding 38.72 to both sides gets me that guy. Now, what does that mean? That means 30% of patients are less than 37.07 inches tall. Do not get confused with how the fact that, you know, X is in inches, the areas are percentages, right? Why don't you take a look at number 5 and see what you would think about that? Definitely start with a curve. All right, for number 5, this is how I started thinking about it. I want to know between which two times will the middle 96% of the visits fall, where, again, the mean time for these oil changes is 16 minutes, and it's normally distributed. So I have this, my normal distribution. I wrote my 16 in the middle, and then I started thinking about, well, what does the middle 96% mean? Like the thought bubble says, that means that 4%, or 100 minus 96%, are going to be in the tails of the curve. So the whole thing, again, remember, is 100%. If there's a middle 96% that we're marking from here to here, then that leaves 2% in each tail. And so, how do I find this leftmost point here, my question mark? What x value is this? Well, that's a matter of exactly as I did number 4, but looking up not 30%, but 2%, isn't it, for that tail? So I'm going to go to my table, and I'm going to look up the area that is 2%, which is, remember, in decimal, 0.02. It's going to look most like that in our table. Well, what's the z value? Go ahead and look, and pause me down, and you find it too. In fact, if you want to, try to complete the whole problem. I'm actually going to do my work on the next slide, so meet me back there. All right, this is what I did. Like I said, I was looking for that value where the area to the left of it underneath the curve was 2%. So as close to 0.0200 as I could get. Turned out that there was an area that was 0.0202. You will see that on the first half of the table. That corresponds to a z-value of negative 2.05, which means, just like on number 4, we're going to use that z equals x minus mu over sigma, sticking in our z-value, sticking in our mu and our sigma, and calculating out and getting x. This is rounded to 1 decimal place, as the instructions said. There are a couple different ways to solve for that next question mark. I think I will do what I feel is the most straightforward, and that is use the symmetry of the normal curve. So here's what I am picturing so far. Whoa, here's my 16. Let's make that less just ridiculously nasty. There is my normal curve. There's my 16, right? Here's the 11.3 minutes, and again, that's that 2% area. Now, if I want the area over here to be 2%, all I need to do is remember that that is symmetric. So the difference between 16 and 11.3 is the same difference between 16 and my unknown value. So let's see, 16 minus 11.3 is what, 4.7? And so let's add that 4.7 to 16 and get 20.7. And though that would have to go here. 20 point, oh, so sorry. Let's erase that. That's such a mess. Okay, 20.7. Now, let's write ourselves a sentence. The middle 96% of all service visits will be between 11.3 and 20.7 minutes. All right. What do you think? Okay. Page 6 is about showing this stuff on the TI calculator. Specifically, we've got this inverse normal command. Let's look up here at the top. It says repeat of example 4. This is number 6. I'm just calling it number 6, but it's what we did with number 4 with that percentile. You'll remember when we did it back there with number 4, it involved looking up as close as we could get that 0.30 in the table. And you will remember that we didn't quite find 0.30. We just had to use the z-value with the closest area we could find, right? Well, that's not the case if you do it on the TI calculators or StatCrunch. So here are my instructions for using the TI calculator. This command is in the distribution menu, so you use the second function of the vars key. You are going to select inverse norm. It's number 3 in that list that you will get. And just like I show here on my calculator screen, you put the area under the curve to the left of whatever x value you're after, followed by mu and sigma. You'll notice I can use the mu and the sigma that I was given. I am not trying to convert through z's with using my calculator. I'm putting in the mu and sigma from the pediatricians. And of course pressing enter, and there it is. Notice that does round to the 37 that we had earlier. It is slightly different because it actually found the exact x value where to the left of it underneath the curve was 0.30. And when we did it with our table, we couldn't get that accurate, could we? So no, it doesn't match, but we know why. We do have information here on how to do this stuff in StatCrunch. In fact, doing number 5 is quite nice and handy when you have StatCrunch around. Go ahead and try that out. Unfortunately, I'm sorry, I cannot do that for you here. Let's go on to the next page and wrap these notes up. All right, number 7, how about you try that out? Draw yourself a normal curve. Again, as always, always take the time to do that. Pause me down, meet me back here. All right, here's what I did for number 7. It differed ever so slightly from what we have been doing. So we've got men's heights normally distributed with a mean of 70 inches and a standard deviation of 4 inches. Find the probability that a randomly selected man is more than 6 feet tall. So of course when I drew this, I have my normal curve, blah, 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 and I got my 70 marked, of course, in the middle. I got my 72 marked. That's the observation I'm interested in, right? But I want the probability that a randomly selected man is more than 6 feet tall. So it is this area to the right that I want. That is how it is a bit different than what we did before. So that's not a worry as long as I keep that in mind. Let's do part B. Calculate a z-score. Look it up in the table, right? So I take my 72 just like normal, and I subtract the mean. I divide by standard deviation. That gets me, looks like 2 over 4, right? Which is 0.5. I look that up in my table, and I come up with the area is 0.6915, but we do have to keep in mind, again, what that's telling me is that this area to the left of 0.5 is 0.6915. but I want the area on the right-hand side, all right, that corresponds to this up here. So, got to subtract it from 100, don't we? Talking about the complement rule once again. So 100 minus 69.15 leaves me 30.85%. So, the probability, if I randomly select a man, the probability that he is more than 6 feet tall is 30.85%. Okay, the next little bit is simply a bit of a definition, and just to use that definition and notation a teeny bit. This would play a role in later chapters, but unfortunately we couldn't get to them this semester. That's all right. Here we have the definition. Z sub alpha is the z-score such that the area under the standard normal curve to the right of z sub alpha is alpha. Draw yourself a picture of this situation, it tells me. I'm just going to draw a little guy here. Here's a z-score. Z-scores have a mean of 0. And here is z sub alpha, some z-score out there, right? And it tells me the area underneath the curve to the right is alpha. All right? So that is just little bit of new notation. You're going to just practice the notation a teeny bit here in this section. And number 8 asks me to, considering this definition, use this new notation to denote our result in the last example. And you will, of course, remember that we were looking at the area to the right of some value, right? So that area was 30.85%, wasn't it? And that z-score was 0.5. So what we would say is that z sub 0.3085, I'm just going to write that area in decimal form, equals 0.5. Again, all we are saying is that the z-score, such that 30.85% of the total is to the right of it, that z-score is 0.5. Number 9 asks you to use that definition. Notice it's asking you to find z sub 0.9. Again, like the thought bubble says, think about what that 0.9 means. Maybe even write a picture of it. Draw your normal curve picture, right? And really try to visualize what they're trying to talk about there. Okay, so this is what I did for number 9. Again, as I suggested, I drew myself a picture. I want to find z sub 0.9, which again is the z-score such that the area to the right of it is 0.9. So again, all of that is shaded to the right of the z-score I'm looking for, and that area again is 0.9. Well, what do I look up in the table? The table only has the areas to the left of these z-scores, right? So really, what I've got to focus on is that this bit here has an area of 1 minus 0.9 or 0.1. So I look that up in the table. And in the table, again, I'm looking for the area that's closest to 0.1 I can find. I do end up with an area of 0.1003. Pretty dang close. And that z-value is, if you look that up, negative 1.28. So that's going to be my answer, that z sub 0.9 is about negative 1.28. All right, that wraps that up, guys.